They're called icicles?
Right at the bottom. No. Right at the...
What's the... I don't know all of the keybinds. I don't know what any of these things are doing.
That's not ominous.
What? The timer?
15 minutes.
It was for the grads last night. They were doing something in 15-minute increments. I don't know, probably data science. That's what they usually do. I taught probability theory last night, right? I was like, I know what that is, right? And then they're like, how do you use this to do data science? I was like, I don't know, what's data science? Anyone know what data science is? No. It's what I thought, right? If you find out, tell me. How's Shaw going?
Bad.
That was fast. Okay, get one of these ones. Yeah, so how's it going though? Did you do this one? Do we need a 1-week extension on Shaw?
Yes. Yeah.
I really want you to do it. Like, it's very, very cool. It is much cooler than the second coolest thing, which is me. It's not much cooler than me. That's ridiculous. It's much cooler than the third coolest thing, which is undergraduates. Okay. No, you're not even going to defend yourselves? You don't think you're cooler than a CS professor. That's a...
You're a student. How could we be?
Yeah.
Because you're not cringe yet, right? You can still be based while you're a student. So, I woke up this morning. Any of you wake up this morning? Can I hear it for waking up every morning? Any rise and grinders? Who else is on their Sigma grind set?
I'm on the Sigma grind set.
Yeah, we're on
That's different. Waking up early.
Yeah, no. I didn't wake up early. I woke up at 11:45. Okay. But I had work until 10 last night, so I don't know. Can I hear it for jobs? Anyone got a job?
Ooh. Jobs suck.
That's correct.
I got 3 of those. That's too many.
Okay, so anyways, where that anecdote was going is I was like, what lecture do I give today if we need the SHA 256 extension? And I thought about it, and I have no idea. So I'm just going to give the lecture that was scheduled anyways, which is for the next homework. Sorry? No, I'm not sorry. You're all doing your homework late. That's not my fault. So anyways, this is probably not going to help you on SHA 256. I think the thing that would help you on SHA 256 is working the number of hours required by the credit hour requirements of the course. Who has spent at least 10 and a half hours on SHA 256? Okay, so that is many fewer people than said they weren't done yet, right? Okay. Put your hand back down. It's not due yet. There you go, right? Disgusting. I should have just made it due on Tuesday. How many of you are going to finish it before it's due?
Wow.
Oh, so that's pretty good. Let's see. Yeah, we don't need a 1-week extension.
I agree.
Lock in. Okay, so you can make up your mind, right? So like either you spent enough time on it before now, and you will finish it on time, no problem, or we need the 1-week extension, right?
Unless the question that you asked of will you finish it before the due date was considered, the due date was considered the next one.
Oh, so I underspecified it.
That's how I interpreted it.
Okay, how many of you are going to finish it by Thursday at, what time does this class start? 2:50 p.m. Pacific. That's not when it's due. Okay, all right, so we need a 1-week extension because even Indy, who's a try-hard, needs that time.
I've spent like an hour on it. You're not helping me, kids.
Are there any good role models in this class?
I'm just
Ben's a better role model.
I'm just here.
Did you finish it?
Yeah.
Yeah.
How long did it take you?
Oh,
Like 30 hours.
maybe not 30, but I probably 20. I
Probably
don't know
20?
to see.
That's why we're in this class.
Right, and now
So it took you 20?
about.
Are you like normal?
Incredible question. I don't know.
Are you normally distributed?
I'd like to think not.
Are you log normal, perhaps?
What do you think it's
What?
So if we take a series of measurements,
Right, that's log.
okay. Means you take a log of it, then it's normal. So it's like if I got hit with a log and then
Right.
went back to acting like a normal person, right?
Oh.
I'll give you a 1-week extension. Fortunately for you, the homework that was going to be assigned this week, I thought was too hard. So there's no real point in having you start that until you finish SAT 256. But this is going to introduce it. Okay, so there's been some jibber jabbering on the DISCI chord, right? Where some of you may know Professor Calvin is a big fan of this little thing called assembly language. And if you don't know what assembly language is, that's no problem. I'm trying to decide how to tell you about it, right? But one of the things that's pretty interesting about assembly language is it's like a different way of thinking about doing things, where all of the assembly commands, which are not quite like functions we write in other languages, they don't really have a return value. What they do is they take usually 3 arguments, and so like the add assembly command takes 3 things, and we're used to adding 2 things together and getting a value back, right? That's weird, right? But in assembly, you take the 3 arguments, and the first 2 are the values you add together, and then the third one is the place you put the answer when you're done. This is the foundation of modern computing, and I was trying to think, like, how can I impress upon you the value and usefulness of thinking that way? And so one of the ways I did that is I said, well, the reason you do that inside a computer with assembly language, right, is because, like, the notion of having a return value, like, doesn't make sense if you're a circuit, right? Like, if I'm a piece of silicon full of semiconductor, and I'm burring and whizzing with electricity, as I do in real life, so in that way I'm identical to a semiconductor, right? So if you do all of that stuff, it's like, well, what does it mean to have a return value, right? Return value is very much something I think of in terms of, like, oh, you've got a command line, or you've got, like, a sentence, right? Sentences have return values. They evaluate to a meaning, right? And so, building up to that, the assignment that this lecture is meant to introduce is big numbers. So we take numbers that are too big to fit in our 64 bits that our computer likes, right? And what that means is there's not a corresponding type that can be that return value of that function, right? We've talked a little bit about how, like, you can't really return arrays from the functions. And there are ways to return arrays from functions in C, and I'm not going to teach you because it's going to let you do things wrong, right? Some of you know how to do it. Don't do that. That's cheating, right? Okay. And if you're cheating yourself, right, out of a good time, right? So, this assignment coming up, I'm going to ask you to write add, subtract, multiply, and divide. And I'm going to ask you to do that without using return values. I'm going to ask you to take 3 arguments. Are they called operands? Mathematicians, are the things we put into operations operands?
Yeah.
Okay. So we're going to take 2 operands, and then we're going to take a third parameter, which is where we store the return value, or the value to which something operands. So we're going to take, for example, like, I don't know, what is it? A numerator and a denominator, and return a quotient. Does that sound right?
Yeah.
Yes.
I'm the best with division on this one, right? This is a really cool way of thinking about things, right? I realized thinking about things sort of functionally and thinking a lot about the arguments and parameters things after I put all of these slides together, right? So this is how far I got over winter break when I was doing this for fun instead of spending time with my family. Can I hear it for families? Yeah, that was a little bit controversial, right? So I basically got this far, and then I started working on the machine learning curriculum. It was very cool working on the machine learning curriculum, saying, oh, at least in the R project for statistical computing, which isn't quite a programming language, it's not quite not a programming language either, right? Like, seems extremely helpful to be able to think about what types of functions you have, and how every operation just changes some underlying data frame that's provided as an argument, right? That's very close to what we're doing here, except instead of having data frames, we just have actual data. There's no frame around it. It's only as organized as we want it to be. There's no language support coming in to save us, right? So we're just going to have 4,096 bits, and we're going to swirl them around a little bit, and at the end of it, we're going to take a numerator and denominator and end up with a quotient. Why did I call this finite? Is 4096 a finite number or an infinite number?
Finite.
Right, that's what I was thinking too, right? And so, like, is the number of values I can store with 496 bits finite or infinite?
Also finite.
Also finite. And how many numbers are there? Is there a finite or infinite number of them? You can see the integers,
Infinite.
the nats,
The classic.
the reals, Rn. Okay, so whenever I say the numbers in this class, I'm referring to the naturals because it's a computer science class, okay? Thought I was clear about that. So, anyways, today we're going to talk about finite numbers of things and how it causes us problems. But we're doing this for two very rich reasons. There's benefits to talking about number theory, and it is possible some of the number theory in these slides will be wrong, and our tryhards in the front row will correct me, and those of you that also know it's wrong in the back rows will simply not say anything and let me suffer. And then in addition to that, in addition to having some understanding of the underlying mathematics that is going to facilitate cryptography, this is also going to motivate a style of thinking that is highly relevant to people that do embedded software, low-level programming, high-performance extreme computing. And it looks to me like this is not the way I would teach machine learning, but I think if you get good at this, you're going to get really good at writing CUDA C++, which is the thing we all want to write when we grow up, right? Can I hear it for CUDA C++? Okay. All right, welcome to class. Can I hear it for class? You all cheer way too much. Okay, so this was going to be called big number. And I was like, nah. And then it was going to be called big natural, and obviously I couldn't use that. And so then I changed it to finite, right? That one was for the people that spend too much time on the internet. Okay, so here we go. We're going to say, what are we going to say? We're going to say this isn't true. We're going to say that's false. Oh, here, let's look at the Cali. Who wants to look at the Cali? Wait, that's not the calendar. Oh, no. There could be secrets on there. Okay. I don't even know if there's secrets on there. Okay. Well, we're here, right? Okay. Oh, no, there's a midterm coming up. I wonder what's going to be on there. I've thought of a pretty good idea for the midterm. You might hate it. You might like it. I don't know. This week, we are getting evicted on the 20th, so you have next Thursday off. Don't be loud about that. That's secret. So here's the line of thinking, right? So we can't have a lab section next Thursday. So I'm going to do an extension lecture instead of introducing Fermat's little theorem. And that extension lecture is going to be on some Podman features. It's going to be this planned lecture. I'm going to move it up. Mounts. So you have SHA 256 now, which facilitates this homework, which will now be due here. We're going to do this lab this week, and then this homework will be due here. Then we're going to do Fermat, Euclid, and we're going to end with big RSA right before the midterm. Okay? Unless we need to move the midterm back a week. I might move the midterm back a week. Are you all going to be here on both the 10th and the 17th? Or that week? Like, it is a week of class, right? Okay. Okay, so tentatively we'll say the midterm's moving back a week. And so we do big RSA right here. Yep. Then we get a review week. Then we do the midterm. Then we come back and do Bitcoin. Right? So we're still on pace for Bitcoin. The question is how much fun stuff we do on the way. Right? Okay. So all this stuff slides back a week. This moves up a week. So we're just going to re-scramble it. Which is funny because this is about hashes, which is scrambling things. And then all of these deadlines are going to slip 1 week. That's okay? I'll figure out a way to get this written down in a way that's clear. But that's the tentative plan. And in exchange for that, you get Thursday off. And what are you going to do on those 90 minutes on Thursday? You're going to work on this class the entire time, right? You're not going to, talk to your friends. Unless you're talking to your friends about big numbers. Okay. All right. So, this tweet changed my life. I couldn't actually find it. But there's some philosophers on the internet, and they talk to each other, and they talk to each other like in public spaces where you can see what they say. And there's apparently this philosophical perspective called finitism, where you don't believe in things that are infinite, which makes a lot of sense if you ever try and model infinity of anything. I kind of feel like the fact that it seems like I can think about infinity suggests that my brain just isn't working correctly. That's been my impression, right? Like, what do you mean there's the same number of even natural numbers as there are natural numbers? That seems like an obviously stupid thing to believe, but in fact, mathematics would have you believe that, right? Can any mathematicians attest that there's the same number of even natural numbers? Yes. Obviously, that's not true. Wait, what?
Depends on if you include zero.
Why does it depend?
No, because then it'd be one more or less.
If you have all the natural numbers.
Alan P. How can you say that?
I thought zero was odd. Okay. So.
Well, zero can be.
Yes, that would make it even, right? So anyways, there's more advanced forms of finitism that claim that some certain number is the largest, right? Which that doesn't do very well with respect to induction. But anyways, someone with a doctorate in philosophy in jest said, "I'm a weapons-grade finitist. I don't believe in numbers larger than 2." And I decided to make that my entire personality, so that's what I think unironically now, right? But I found this trick, right? We're using only numbers that are smaller than 2, specifically 0 and 1. You can place these things inside arrays, and then you can use it to simulate as if there's numbers larger than 2, right? And those things are called basically uint64ts, right? So, how do we understand this? I think there is this sort of unfortunate for understanding how computers work problem, where very often the numbers that we use in our everyday life do in fact exist in computers, right? 6 billion is a number in a computer, right? But it is very hard to model Googleplex. Now, we just about never use Googleplex, so that's fine, right? But there's also fractions that are very small that are very hard to model. No one has ever put pi in a computer. It's actually provably impossible. We're only working with approximations. I don't think anyone cares, right? We don't care that it's approximately pi, right? But pi is not in there. You can put in the formula that would return pi, right? But you cannot actually evaluate it, right? Is this controversial? Are people sneering at me?
I just think putting pi in your computer would break it.
Just represent it as a fraction. Just represent it as a fraction. The circumference over the diameter.
A slice is still going to hurt your computer.
Do you say circumference over the diameter? Okay, how are you expressing those things in infinite precision?
As a ratio, obviously.
So perhaps a member of the rational numbers?
Exactly.
So your claim is that pi is a rational number?
Yes.
All right.
It's a ratio.
So is Professor McNicholas in her office right now?
Please don't.
I will send you to the principal's office. So I think I'm going to make some claims about rings that I've since learned incorrect, but I have my fact checkers here, so they'll let me know if or when it becomes wrong. And we're also going to reintroduce the standard int technology. If it seems like I've been talking for a long time before starting the technical content, yes. Okay, like this is like an inherently philosophically relevant lecture. I don't really know a way to go about it without, like, finitism and infinitism are like interesting ideas. Like, so what are the integers? We all know and love the integers, right? It's the natural numbers and also the negative natural numbers, and depending on who you ask, also 0, right? But of course, in this class, 0 is a natural number. Does someone in this class know why we denote the natural numbers as z?
It's a German word for integers.
It's just German.
Something to do with German.
Something to do with German. But probably denoting that predates the existence of Germany, right? Okay, so I don't use the integers very often, and it really bothers me that computers want me to use the integers. And I can give you an example right now. I'm going to press a key on my keyboard. It's this one. This may look like I pressed the Windows keys, but actually this is just my host system for Linux, right? We can open the terminal. My computer seems to be having the same kind of day I am. And this is an example we saw previously in this class, right? So we can take some number like x, and we can denote it using weapons grade finitism, so only zeros and ones. And then I think what we found is we can do this, and we can also express that as binary, right? Okay. Nothing here even remotely makes sense, right? This makes sense vaguely, I say, under sort of the 2's complement formulation, where we just toggle all of the zeros to ones or something. But that is, this thing flips all of the bits, which we can see here. So that's 11001101. So that 1 came from somewhere. But there's a negative sign here. I just fundamentally really don't want Python to turn my information, which I'm expressing as just bits. I'm doing my level best to just type bits into Python here. I don't want it to decide that that represents a negative number. That doesn't make sense to me as a cryptographer, right? I expect this operation to do something, yes, but I don't expect it to add the notion of whether this is a positive or negative value, right? I don't like that. That's not a thing I want my computer to do. I don't know, for example, if this changes the bit length of the numbers. For the record, I'm typing correctly, but my computer's lagging, right? So that's 8 bits. Well, let's try another example. OB. Okay. Y equals. But by the way, do all of you do this where you use the R assignment in Python after you've been writing too much R? Is that? I like this so much better. I don't know why. Okay. X dot bit length. My keyboard feels like it's underwater. What is going on there? I don't get it, right? Like, if I have 6 bits, and they are these 6 bits, how do I know if it's negative or not? That's 7 bits worth of information. And, like, I don't know. I don't like it. Anyways. I like the naturals. So the counting numbers starting at 0. Fight me. Okay. So one of the great things about the naturals and the integers is we can construct them from each other. I'm going to do this in Python using iter tools. Are the naturals and the integers both examples of a field? The natural numbers are not a field because they...
The integers are not a field either.
The integers are not a field either.
They are.
Okay. So I guess I should just call these things sets until I figure out what they are, probably.
They're rings. Ring works.
They're rings, okay. So this is called... So that's wrong. That should be rings. Okay. From iter tools, import count. Are you all familiar with generators in Python? So the way a generator works is it is a Python object. There is no equivalent of this type of object in C because there's an infinite number of numbers in count. The way we can view these infinite number of numbers is with next. And next keeps track of what the last number in n was and then gives us the next one. That's what next means. Okay. So these are the natural numbers. And we're only going to stay here until we get to the largest natural number. So just sit tight for just a moment. Okay, I've realized an obvious problem with my plan. Okay. Of course, there is a clear way here to conclude how you can get modular natural numbers. these things all happen to be between 0 and 9, or no, between -1 and 10 exclusive, 0, 9 inclusive, right? Okay, so this is where modular numbers come from, right? We can generate the integers from the natural numbers, right? And so, as you know, there's the same number of positive numbers as there are positive and negative numbers, right? And we can demonstrate that by using count. So I have this little expression here. I'm going to make the integers. I'm going to make the integers using a lambda function over some input value. So that input value is going to be, so I don't want to say n because that seems like that would be all of them. So I'm going to say over I, well that's the imaginary number, we'll say n. So we're going to take a lambda expression over n. And it's a simple enough matter to take an infinite sequence of positive numbers and turn them into all positive and negative numbers, right? So for each positive number, we're going to need to take two numbers. So I'm going to divide this by 2, so I can have two numbers of the same value. And when I do this, for example, if I took this over the natural numbers right now, I'd say 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, right? And this would continue for some time, right? Then what I do from here is half of those numbers have to be negative. And there's a way to tell if each one of my n values is negative. I can simply say that every other of these values is negative, so I will take n% 2. So I'll check to see if the n value is even or odd. And so this is 0 or 1, right? What I really want to do is I want to be able to take this value and use it to change the sign of this value. So if we think of this as one expression times another expression, I want to multiply the magnitude by the direction. Any physicists? Yeah! Is that physics?
Sure.
I love that. I love your enthusiasm. If it weren't physics, what would it be? Something else. Yeah, the set complement of physics, right? So I have a value ranging from 0 to 1, or ranging over 0 and 1, right? Because they're only naturals, ints, whatever, right? I'm going to multiply that by 2, so this toggles between 0 and 2. And I'm going to subtract 1 from that, so that it changes between 1 and -1. And this is going to encode my sign value. So for example, I can take any given natural number, like 7, and it will correspond to a number in the integers, and in fact it will correspond to all possible numbers in the integers. So I can create a generator, which is equal to z, and that is going to be equal to the make z of n for n in count. And then I can look at all of the various z's, right? Now there's going to be a problem here. I have 2 zeros. But otherwise, I have all of the integers here. And so I think I'm just going to keep going until I get to the highest integer, right? Oh no, I realized I don't have these problems. Right, okay. Okay, that all makes sense. I can convert the naturals and the integers back and forth into each other. It's not even hard, right? Or was this hard? Okay, that's what I thought. I don't like this, so we can just start this at 1. And then we can say next z for z in range 10. 4. And ta-da! It's the integers. Shout out Germania. Good language group. Okay. Anyone love Beowulf? Can I hear your best Beowulf awoo? I'll go first. Awoo! Okay, your turn.
That's on the internet.
That's like the 8th least controversial thing I've ever said. Okay. So I have a citation for 0 being part of the natural numbers. It's right here. So stop arguing with
Well,
me.
you also said first, obviously they think that.
Who do you want me to cite? I love how little this is. Isn't it cute? Like, it's like the wrong size. So I think of the uints, the unsigned integers, as being very close to the naturals. Perhaps this is an unnatural way of thinking of things, right? My religion is very strongly that all numbers are derived from the naturals in various ways, and naturals are constructed from sets. You don't have to agree with that. It seems like in computers that is uncommon. It seems like the computer people very much wanted there to be unsigned numbers. Perhaps they didn't know about modular arithmetic. Perhaps they didn't take their Turing vitamins. But anyways, to me it is fundamentally unnatural that I have to specify that I don't want a sign bit using U. I hate that. I hate it a lot. I will hate it forever. I'm sorry. That's why I always use uints. How many of you think of, when you think of numbers, and I just mean numbers, like the linguistic term, do you think of them as including negative values by default? Thumbs up for yes, thumbs down for no, thumbs to the side for I always think of the complex values. Can I hear it for the quaternary?
Quaternions?
Yeah, anyone think of those? That's what I thought. Okay, so we have a problem, and the problem is that there's numbers that are big, right? Can I hear it for going big mode? Stop cheering. Okay, this is getting weird. Okay, Python has been lying us for years that its integers have no upper limits. How long? How many years? Only in Python 3. So in Python 2, they didn't lie to you. They started lying to you in Python 3. What year did Python 3 come out? Nobody knows. December 3rd, 2008. So Python started claiming there's infinite numbers the same time as the financial crisis. That's why I don't have a real job and had to go into academia, because of Python 3. Okay. Is that true? Is that what year there was a financial crisis? There's a financial crisis every year. We don't need to worry about that. Okay. Okay. So we could say there does not exist n such that n is not an element of count. Count is not exactly a set, right? It's a generator. It is a automata that produces values within the natural numbers, right? But we could say that the set of values that count creates, we could treat that as a set. So I'm abusing my set notation here. I don't think that this is mathematically proper. Really what I should do is, the way this is often expressed in automata theory is you say the language of something. So count produces some symbols or some collections of symbols, and that is the language of count. The language is a set. It is the set of things produced by count. So I think I should specify the language of count here. I thought that was more confusing, so I'm saying it out loud, and there will be no evidence of it as soon as I go to the next slide. I thought we would pick a pretty small, pretty large number, so I picked Googleplex. Does anyone else have like a pretty small, pretty large number that they like? I've heard these things called infinity scrapers, which is odd because that's not particularly close to infinity. Actually, this is much closer to 0 than it is to infinity, right? Okay, so let's go ahead and throw Googleplex in Python and watch my computer melt. What's this flag do? Understanding check.
Runs it.
That's so specific.
It's C for Ohio.
Goodness me. Okay. So Python accepts a series of possible command line parameters, right? If I provide no parameters, I get something terrible. The Python interpreter, REPL, whatever, read evaluate. What's the P&L stand for? Pumpkin lice. Okay. All right. So that's the bad thing that Python can do, right? Wait, no. I'm in. Do I have any Python files here? No. So I don't have any Python files, but if I did, I could run a Python file, right? But those aren't the only things we can do. And one of the, I think, next most obvious ones is there like a help command, right? There's also version. So there's all kinds of other things we can ask Python to do other than just running Python scripts, right? And one of the things we can do most easily is just directly run a little snippet of a Python program directly at the command line without going into the interpreter. There's a variety of reasons you might want to do this, the most obvious being automation. right? So if you have a script where you want to do a little bit of Python, but you don't want to necessarily save a .py file or enter the Python interpreter and start throwing things into that. It's just a little bit too easy to run a little bit of Python directly at the command line. And so the most obvious one is print hello world. Have you all seen this before? You've seen this before. Surely I've shown you this before. How do you spell world? So like, what's this going to do?
Print hello world.
How is that different from this? And how is that different from this? And I'm sorry I'm using PowerShell, right? Here, we'll boot it. I don't know why I'm using PowerShell. So, this is one way to run Python stuff. Oh, you can perform multi-line calculations? That's how you spell calculations, by the way. Take note of this U. Okay. I'm putting the U in calculations, right? Okay. You can do multi-line Python using semicolon. Did you all know this? Is this common knowledge? So, I don't know, what's an example of multi-line Python? Nice. So, you can do multiple lines of Python. So, I have no idea why everyone's ever saved a .py file, because you can simply save this as a .sh file and then run it that way. So, I'm going to do it. Was that my computer that made that noise? Is this thing not muted? Okay. So I think I can say, is that fine? Okay. So there's a variety of ways to work with Python. One of the benefits of working with Python directly at the command line like this is that we can see how fast it is without using Python internals, which we might want to do so we don't have to import a library. Let's do an example. We can do time. If anyone knows how command line works, is this going to work? So I can evaluate how long it takes Python to do something, right? And this is a productive use of my time. I like doing this for fun. How many of you started like timing how long it takes code to run in perhaps algorithms, something like that? Yeah, right. So this is my preferred way to characterize time. Do all of you in algorithms use like time it or something, or?
There were a couple different ways to do it. We used time it at some point, I remember.
Okay, yeah, and nothing against time it. I have a tendency to like to use time. Why? Because I'm always racing my Python against C. So I use something that isn't built into Python or C. And so we can do some things here, such as say, we can see if from iter tools import count, 0 in count, very fast. And we can check increasingly large values to see if they're in count. We can check to see if 10 is in count, even faster, right? And so what's this suggesting? So like, what's all of the time happening here? Well, there's a bunch of things that happen every time I run this expression, right? I have to go find out where iter tools lives inside Python. I have to go find out where count lives in iter tools, right? I have to figure out where 0 lives. I have to figure out where the expression in, which I'm guessing this is implemented as a function internally somehow, and then this is a generator, right? So I have to start applying next to the generator. And over time, we can put increasingly large values into count. And we can see if it starts slowing down. It's like, oh, is it maybe slowing down there a little bit? I don't know. What do we think, right? So, oh no, this should be 10 times slower, right? So that's just an emergent phenomenon that this is a bit slower. It's a bit odd to do things this way. So I'm instead going to use shifts, and 1,000 is about 2 to the 10th, so it's going to be about this big, right? And I can put increasingly large numbers in here through the bit shift operation. And it's now much easier to make this size go up really fast. And in fact, we can get things to start slowing down at around 1 million, right? That's still fast. You can do a little bit of binary search here, right? And you see, oh, we're starting to slow down at 2 to the 18th, but perhaps not. at 2 to the 17th, right? Those of you following along at home should be extremely suspicious that when I put 2 to the 16th in here, it's still almost instantaneous. And as soon as I go over the size of a 16-bit integer, this thing slows down by a lot, right? The difference between these two values, right? This is 50% more than that one, which means this is, I think, 2 to the 17th, right? So this is just a little bit bigger than a 16-bit integer, right? That is half of the amount of time it takes to import itertools an entire Python module, right? So that is how much your computer slows down when you go over to size 2 to the 16th in Python, right? You've probably never felt this. I don't know. I found it quite remarkable. So what do we have going on here? Well, you can run this on Linux. Are you still using Podman? I'm going to give you some tech to use Podman a little bit better in the bonus lecture next week. I'm getting really into running things directly locally on my, whatever my host system is, Windows or otherwise, and just having commands get injected into Podman containers and come straight out through mounting, which is pretty nice. So anyways, you can do this inside Podman. Right. Let's put in some bigger numbers and blah, blah, blah. Here's my table I made. What you have me doing here, right, I'm using 10 to the n. That's kind of cursed. So let's just let's put some bigger values in here. See, I think we put in 20 and it was slow, right? That's pretty slow. Why is that not full screen? And I think we can get pretty close to taking forever pretty quick. How long do I think is this going to take? Like 8 seconds or something? This is, I don't know, 9 seconds is not that bad, right? And maybe you don't know how big that number is, but that's no problem, because we can print 1 to the 28th and just see what that number is, right? So Python's able to calculate this number very quickly, right, in the same amount of time it takes to start up and do anything else. I don't know how much faster this is if I don't import itertools. Guess it takes 0 time. But this is offensively slow performance on a very, very small number, right? Which would suggest to me, and it does in fact suggest to me, that Python doesn't have anything even close to infinite numbers, right? We noticed, and I pointed out and I showed to you, a performance dip as soon as you go over 16-bit integers. That is very small. I can count to 2 to the 16 probably in a week, right? Not that I've ever tried. How big's 2 to the 16th?
65,000 something.
Yeah, right. And I think I remember, like, how long does it take to count to 1,000, right? So you can probably do it in a couple minutes. So 65 times a couple minutes. I could probably do it before dinner tonight, right? Easy. 65536, maybe, is that right?
Yeah.
Can I do arithmetic in Bash? Probably, right? Like,
Yeah.
not easily.
You have to echo, and you have to use a couple specific things to do it, because everything is a string.
I have a plan. I realize that there is a way I can do it in Bash. Okay, and so, and then what you have to do, you have to use the cringe quotes. Really? Oh, I see. I played myself there. That one was obvious in hindsight. Okay. There you go, 65536. Okay. So, I did some calculations here. And I did this in base 2 with you all because I trust you. But here it is in base 10, which might be a little bit easier to think about. I did this on my home desktop, which is dramatically faster than my laptop, which is currently hot to the touch, which sounds like a sick single for like a cool emo band or something, right? I saw an emo band on Friday. They were sad. Okay. They made me sad. I was like, oh, I'm so sad. Right, okay. Anyone going to see MCR in Seattle?
Yeah.
Yeah. Just sneak in, right? Did you pay?
I didn't trust that I could sneak in, and I didn't want to miss the chance.
That's reasonable. Okay, we'll get you in somehow. Yeah, I know them. That's not true. I should just start claiming I'm in NCR. No one would know. Okay. So here's some calculations, and I want to talk you through all of this because you should be thinking about these things this way, right? So I just did powers of 10 here, and I noticed that I basically got no change in performance until, wait, 10 to the 5th is 10,000. 10 to the 6th is 100,000. 2 to the 16th is right between these numbers, right? So this is the same performance when you go over 2 to the 16th, right? So clearly something in Python internally is using 16-bit numbers, which I didn't know. I thought they only used 32 bits. I didn't expect to see this. I was quite surprised. We're not, so this, don't trick yourself here. It should not take twice as long to go 10 times more numbers, right? That's weird. This thing, 167, is about 5 times bigger than this thing, right? But this number is 10 times bigger than that number. So we're not increasing linearly in how big our numbers are until right here, right? 16, or 160 to 1500 to some large number, 17,000, right? That is now increasing directly in proportion to how much bigger the numbers are getting. So I'm claiming at this point in time, I detected linear cost with respect to the size of the value, and that kicks in starting right at 10 to the 7th, which is a little bit past 2 to the 16th, right? I'm saying I detect this pattern here, and I was saying I was unwilling to take measurements that were dramatically larger than this because I expect the next measurement at 10 to the 10th to take 3 minutes. And I can't spend 3 minutes doing anything other than watching Subway Surfer TikToks, right? So I'm claiming that I expect the time cost for 10 to the 10th. I think this is actually wrong. I think that should say 8, right? That's a little bit too close to going over something. But so I think that taking the time of 2 to the 10th on my desktop, which I don't have today, and my laptop is 50% slower. So on my laptop, I expect this to take 210 seconds to... can I multiply that by 1.5 in my head? No, I'm going to do 8. So 210 to 270 seconds. That's a long time just to see if a number is in some values, right? And so I'm going to claim that the time to do any 2 to the 10th is described by this formula. I discount the first 9 as instantaneous, so I can essentially do 10 to the 9th per second, right? And then I'm going to multiply 14 to 17 times that. And this means that I can calculate how long I think it would take to check to see if a Googleplex is in count. And I think it's going to take a Google minus 9 seconds, because a Googleplex is 10 to the Google. So I'm going to subtract 9 from Google, which is exactly the same number as Google, actually. That many seconds. And I think that's 316 novemvigintillion years, according to a search bar. Do you all track that okay? Do you see the operations I'm going through here? Does this remind you of algorithms at all? Okay. C is for clear. So the great thing about C, the C programming language, the good programming language, the language which I love, right? This is actually my first language. I learned English when I was 7 after speaking C89 specifically for years, right? Because I was born in 1992, so C99 wasn't out yet. Can I hear it for 90s kids? Yeah, that's what I like to hear. Okay. So if you want to calculate the maximilian of your language, you can simply do that in C. You can just add something to this until it stops getting bigger. Let's run this code. What else are we doing? Anyone have any hobbies? Me neither. Okay. What do I call this? Max.c? So it occurs to me I made an obvious mistake, which is that's not going to increase the numbers very fast, is it? That's okay, it's C. It's way faster than Python. This seemed to be running around 15 times faster than Python. Anyways, that's, what's that? That's 2 to the 32 minus 1, right? Does that look right to us? Any 2 to the 32 minus 1 appreciators? Okay, fine, we'll check. So I can actually just calculate what the largest number in a C-type is, and this isn't that difficult at all. Where's my cursor? How does Vim work? It may come as a shock to you that you can also use semicolons in bash commands. I wonder how long this will take. Did I do anything that should cause this to take a very long time? I expected it to be done by now. Cat max.c. Oh well, guess we'll never know. Okay, so, for me, let's see, I timed this on my desktop, and it took 5.19 seconds to capture the maximum value of a uint32t. And on Python, it took me 70 seconds to do the same calculation, which I did test, right? This is 70 seconds, this is 5 seconds, that is C being around 12 times faster than Python, right? We're thinking about that. So if it takes 5.19 seconds to count to the largest uint32t, how long would it take to count to the largest uint64t? And think about it. Actually, talk to your partner. Figure this number out. Discuss the rest of these things with your partner. I want you to think about this stuff. I'm going to walk around. I'm going to talk to you. I'm sorry. I'm going to talk to you. Okay.
One more.
Talkity.
One more. Yeah, 42. I thought it was going for. But I feel like, it's like I want to believe in C. You know, it did that hella fast.
Time before was figuring out what's
Oh, no, I know, actually.
32 becomes 7.
But I do think it'll be quick.
That's, yeah, a little more than
Wait, well, okay. Because how long would it take in Python? And then C is appearing to be about 12 times faster.
how with the magnitude.
It might not be, but it's good.
That is a thing that happens in the courses. It goes right here.
I think it would be.
I don't think that's
two different git
I don't know. I feel like it's going to take a surprising amount of time either way. I think it's either going to be yes it will. Yes it will. So we have a lower value. There we go. Okay, but imagine it doesn't.
Well, there's no.
What then? Yeah. What? Aha! Clearly, you have have made a miscalculation.
Well, because when I'm doing
It cannot match.
What's the difference? There's only one.
Clearly an amateur.
There's an extra byte.
The EOF character. Yes.
But that's not the end of the file.
Or it was like a line break character that was only present at the end of the file, but not like if you put the exact same code. What I didn't fix it is I just when I was adding the one, I just added it as the last bit. But Indy, wait a minute.
The tester is expecting.
Yeah, the tester's expecting it, and typing in like SHA-256 sum does it with the line break. So even if yours is correct, it will not match the output of the JavaScript one. That's just helpful for like visualizing.
So 51 divided by 8 is 8.5. So 2 of them is less. So where the fuck is this coming from? Because this number is never going to be bigger than 62. So I'm going to use two things. Right after this is and he's doing it like in the middle of it. Which I think is fine because if you only really if I think that destination is first
Destination was first.
Oh, nope. Okay, I noticed something wrong. I'm using value on truck user overall. Also just reduce this. So if I replace this with a 90 cents, or just J, they're off.
You can use a J for instead.
I'm going to use a J because I think I'm less likely to break that way. I'd like to replace it with digit, but I'm really starting to use it like I want to digit numbers.
I think that's nice about those is that you do the work set and you got the architects right here. You know what you'll be right. Here's another architect. So you're returning. Yeah. You do together. That's good. Yeah.
Oh.
I'm already doing my PSI. There's no point in that. Okay. I'm actually getting so I don't want to come out with a major and so and also yeah, I'm happy to PSI. Software engineers require that and like not physical forms. This is actually not yeah. That's where it's going. But and I already had a hard time with foundation.
I guess that blind is probably close. Or maybe the sun has moved it. Crazy. I'm really excited to do my modern homework, bro. That's like the one big thing weighing on me and showing me.
I'm ready for all these applications to be done, and all the ones that I haven't done. I just don't get a chance to do them.
Yeah, same. It's a lot. It is a lot. Like, yeah.
Once it's done stuff.
When are those deadlines approaching? Are you gonna be doing this for another month? What's like a realistic timeline that you expect stopping applying every day?
But after like February.
Okay. That's doable. You got that. And we have not 280 versus 1. Are you ready for that?
So that goes stays on the scale.
Yeah. Thank you, 331 Brown.
There's no way Josh let us do it. There's no way Josh let us do it.
It says though on the at least we might have to find the determinant of a 3x3, or at least like explain how to do it. Because in the last time I checked in the quiz topics, it says that one of the things we have to know is like the way to calculate a determinant for 2x2 and 3x3. Yeah, it sucks.
I mean, it's a lot more than I expected on this side. It's a lot less than I thought.
That astute observation. Have you been working on the modern homework, Indy? Me neither, but I've been working in the shop. Which now, I guess, now first yeah, I guess you're right. Literally, it was a game of chicken. And I lost because I did the assignment. But that's fine. I'm glad I did it.
It's like the right, this is one. This is how to I figured out like all order roads
Maddie's school has a lot of resources, and her friend, who is Italian, which will be relevant, and a journalism major, just got approved for a scholarship for a 1 month long expenses paid like journalism trip to Italy. And it's like literally, she's been learning Italian, and now she gets to go for free per month, all expenses paid, to do her major. That's so stupid. That's so awesome. I wish that study abroad programs made more sense for computer science, because that is something that I would have really liked to fit into my experience, but it's just, for a variety of reasons, will never work out. But especially like where I can do the same thing here as I can in like Shanghai or like Belgium. Like where am I gonna go?
So, and then the register, one day, I showed this one day that took me 4 months, 2 months to debug. It's this thing. This is actually a single entity. This is right now. Normal users. I don't want anyone else in the especially with my portfolio website. Yeah, but I never filed it.
So, stupid like, so this is, every single one of these functions corresponds to.
Nope. There's actually an email asking for people to post threads, which means that they are done. But we get 2 math entries, so lucky us. Yeah, 2 days. 2 days. You don't really want to jerk it. Don't even worry about it. I'm on my own.
Okay, I have 4 bits. I can put 1 possible value here, 1 possible value here, or 2 possible values, 0 or 1, right? So the number of possible values I have is 2 times 2 times 2 times 2 equals 16, right? 16 is 2 to the 4th, so I can take 16 possible values in something of size 2 to the 4th. Which means if it takes me 5 minutes to do all this stuff, I can do 16 things for 5 minutes, right? If I take 32 of these, right, or let's take 8 first, right? If I double my number of bits, I do not double my number of values. I increase it exponentially, and I increase it exponentially based on how many values I had initially. So what I'm actually doing is I'm taking this 4 and doubling it. I'm not doing anything to the 16. The 16 has a built-in exponential base. So this thing has 2 to the 8th possible values equals 256. 256 is 16 times bigger than 16, right? Equal to this squared. Now, so then you might think, oh, well, every time I double my number of bits, my number gets 16 times bigger. Not true, right? Because 2 to the 16th is this monstrosity, which is 256 times bigger. So we're increasing along an exponential. You all know what exponentials are. The important thing to keep in mind is the difference in that 32 and 64. That's referring to how much information you have. When you have more information, you can store exponentially more unique values. 2 to the 64 is 2 to the 30 times bigger, 2 to the 32 times bigger than 2 to the 32. So, what this means is if in 5 seconds, I can do 2 to the 32 of something. So I have 2 to the 32 per 5 seconds, right? And I need to see how long it takes to do 2 to the 64 of something. So, I do this many per second. I don't evaluate this. We can call that y or something. I have 2 to the 64. So, one way to do this is to figure out how many times I have to do this thing once. And I do that by taking 2 to the 64, dividing by 2 to the 32, which equals 2 to the 32. So I have to do this thing that takes 5 seconds 2 to the 32 times. Perhaps we view it as 5 seconds per 2 to the 32 value, right? And I'm sorry, that says 32, right? So what I need then to do 2 to the 64 of something and I know how long it takes 2 to the 32 of something. That gives me 2 to the 32 times longer. So I'm going to take 2 to the 32 times 5 seconds. This is equal to 4 million times 5 seconds, which is equal to 20 million seconds. A million seconds is, well, let's see, what that's about actually a million minutes, right? There are some large number of minutes per day, but not that high, right? But this is some number of years, right? How many years is 20 million seconds?
20 million seconds? Or
Yes.
Seconds is 0.6 of a year.
Okay. So that's a long time. How long would it take to see how big a uint 33T is? This is twice as large. If I have this down as 10 seconds. The uint 48T type is used sometimes. This is 2 to the 16 times bigger than a 2 to the 32, so that's 2 to the 16, which is 65536 times 5 seconds. So it's this times 5, which is 300K seconds, which is, that's not bad, because this is 5 minutes. So 5,000 minutes is like a week or something, not that long, right? It's extremely unlikely that your Python instance is going to last that long, right? C programs do last that long if you write them without malware. And I haven't taught you how to write the things to cause C programs to crash. This is not an information theory class, but you probably should learn information theory at some point. It is helpful, especially when you're looking at SHA 256, to realize you're just dealing with information, and that information has some certain size. But if the size of that information gets bigger, the number of unique values increases exponentially. This is why, essentially, everything ever put in a computer has a different SHA 256 value, because no one has put 2 to the 256 different values in a computer ever. That doesn't make sense. Every permutation of every spreadsheet, there's just not enough information to have distinct, or to have overlapping SHA 256 values. And if, for some reason, what you're doing is you're hashing some probably LLM scale training data set, right, which would be the thing that would be big enough to have this many permutations, then you simply use SHA 512, and it's not twice as big, right?
Oh, no.
It's 2 to the 256 times bigger, right? That amount of information just, like, there's no way you could have that many different possibilities, right? 2 to the 512 is, essentially we take 2 to the 10th, and that's equal to 1,000, right? So that is 1,000 to the 50th, which is a 1 followed by 15 or 150 zeros, which is not 50% bigger than a Google, right? It is half a Google times bigger than a Google, right? It is a Google to 1.5 power. So these are comically enormous numbers, right? These are larger numbers than anyone could ever possibly deal with. Except, of course, if you're using the power of the C programming language, which can totally handle them. All right. Instead of calculating these manually, you can look them up. You can also use a little trick I like to call subtraction. You can subtract 1 from 0, and that will instantly give you the largest number in any bin, right? These things are rings. Is that right, math majors?
Yeah.
The uints?
I think
Is the current field so 0 is divisible? It would be an integral double.
Okay. Because they're ints.
Or would it be?
Right, so you're not allowed to have 0 divisors in whatever a field is, right? And every one of these things is divisible by, 0 is divisible by the size of the field over 2, and you raise 2 to that power. So in a uint 32, 2 to the 16, if you divide 0 by 2 to the 16, you get 2 to the 16 back. So the square root of 0 is always half of the size of the thing, right? More or less, right? And I think this is the huge nerds approved modular notation. Gotta watch out for you huge nerds. Okay. Look out for extremely annoying things. If there are two values that are within a uint, that does not mean that their summation is larger than them. If I add 200 to 200 in an 8-bit integer, right, that is 400. 400 is larger than 2 to the 256. I cannot express 400. So some modular operation occurs there. Multiplication is much more interesting. With addition, you might need 1 additional bit. With multiplication, you might need twice as many bits. 16 times 16 is 256. You can store 16 in 4 bits. Well, 5. You can store 15 in 4 bits. You only need 5 to store 16. And 16 squared cannot be stored in 8 bits. It's too big. Let's look at an example. Should we go ahead and run this? Have you seen A2I yet? No, you haven't. Here it is. Lucky you. Congratulations. How long till class is over? Okay, we got 10 minutes. What's this thing called? num.c. What is in num.c? Oh, that's not too bad. Okay, we're using 8-bit. We're using 8-bit values, okay? All right, so we're going to take a dot out. We're going to add 2 and 3, and then we can see what the return value is with echo. So let's take, I think the example I gave was 200 and 200, and then we will echo the return value. Oh, that's cursed. What's happening there? Is that what I expected to happen? No. Okay. Did I break it? Oh, I said echo instead of a dot out. Never mind. Okay. Okay. So 144 is, of course, 12 squared, right? And why is it 12 squared? I have no idea. But anyways, so if we add 200 together and our maximum value is 256, we get 144 back. Why is
456.
Yes, but why is 2 to the 8th plus 2 to the 2nd times 3 equal to 4 times 10 squared? That feels odd to me. Okay. Anyways, it doesn't matter. So here's some values we can check. uint8t is finite, and we can see the finitism using this. Ooh! Oh, this is not the approved way to denote mods. I'm supposed to put this in brackets, right? So that's a subscript. So
That's n mod 2d8.
yeah, that's how I'm denoting that. And I think your preferred way to do this is n open bracket 2 to the 8th close bracket. Or oh yeah, you do backslash, right?
N mod parentheses 2 to the 8th. N backslash. You use z usually instead of n because it's
Where's that like LaTeX fast? Quick.
Well,
So I want is this what I want? Oh, it's parens?
Yes.
That in parens?
No, just parentheses.
Only parens, not brackies?
Should be parentheses. Oh, that's
Oh no, this slash is the wrong way, right? Is it? It's this thing? Wait, is it?
yeah.
That's what it should look like?
Usually you use z instead of n because it's the same thing.
No, not in a CS class. No, you use Z in a math class. That's fine. We're not doing that here. Get out. That's no bad. Okay. Sums and products are weird. Why does that matter? Well, we're about to do sums and products. Okay. So, what this is all leading up to is the notion that we have to deal with integers of size 4096 bits. Why is that? Because GitHub says we have to, and they make the law. Okay. Now, some of you who are huge nerds may notice that there's something about elliptic curve cryptography here, but we are currently using a legacy system that doesn't support that, right? So we're using RSA. And some of you may have heard that you're not supposed to end sentences with prepositions. So it's easy to reformulate this. You say, for what does that 4096 stand? Was there something wrong with that? That's fine. Okay. So one way to do this is to use SSH keygen, which is the sort of open source industry standard technology for generating cryptographic keys. It defaults to 2048 right now, it looks like. Can I hear it for 2048? Any 2048 appreciators? Yeah, that's what I thought. And so what we're going to do over the course of the coming weeks, months, years, and decades is we are going to use these ints to implement arbitrary high-precision integers, their arithmetic operations, and we are going to talk about their function types. But we are out of time for today. I think I made you think pretty hard, so I'm going to call a natural cutting point here. We will resume. I will finish this lecture on Thursday instead of launching you on a homework before you have the week off, and then we will get back on track for lectures in the coming weeks. Take an extra week on SHA 256, and please do it. It is cool. It is cool and fun and good. Please. You will want to have done it in the future if you don't do it now. Okay. Thank you. See you around. Do any of you need to talk to me about anything?
I think it's something like that.